Today we're diving into 5 principles that can take your code from a fragile mess to something that's actually robust and built to last. They're called solid, and they're all about making your software easier to understand, more flexible, and way more maintainable.
You know that feeling, right? You've got some code, and it works, but you are terrified to touch it. Because you know that one tiny change over here could make a completely unrelated feature over there just collapse. Your codebase has turned into this fragile house of cards, just waiting for the slightest nudge to tumble over.
So what's causing all this chaos? Well, it usually comes down to something we call tightly coupled code. It's when different parts of your system are so tangled up together that you can't change one without affecting a dozen others. This makes everything rigid, making every new feature a real struggle, and frankly, a breeding ground for bugs.
But hey, there is a way out of this mess. Way back in 2000, a software engineer named Robert C. Martin, you might know him as Uncle Bob, put together 5 key design principles, and together they form the acronym SOLID. Think of it as a toolkit for taking apart that house of cards and building something strong and stable in its place. So where do we start? Well, the solid journey begins at the most fundamental level of our code, the individual classes. The first 2 principles, the S and the O, are all about making sure our basic building blocks are strong and reliable from the get-go.
The very first problem Solid tackles is something you've probably seen a million times, the God class. You know the one. It's that one class that seems to do everything. It's handling business logic, it's connecting to the database, it's printing invoices. It's just a recipe for disaster. And that brings us to our very first principle, S for the single responsibility principle. The rule is incredibly simple. A class should have one and only one reason to change. Look at what's happening here. We haven't lost any functionality, we've just organized it. The shopping cart class now only worries about shopping logic. If we need to change how an invoice gets printed, we only have to touch the card invoice printer. This keeps our changes isolated, and that dramatically reduces our risk.
Okay, so our classes are focused. That's great. But what happens when you get a request for a new feature? Our first instinct is often to just dive in and start modifying code that's already working. But that's so risky. Every single time you change code that's already been tested, you're rolling the dice on introducing a new, unexpected bug.
This is exactly where the O comes in, the open/closed principle. It says software should be open for extension, but closed for modification. Look at the solution on the right. We don't crack open our existing code. No way. Instead, we create a common persistence interface and we add a brand new Mongo persistence class. We've just extended what our system can do without ever touching and potentially breaking the original code that we know already works.
All right, next up is the L in solid. And honestly, this one is maybe the most subtle of the bunch, and it's probably the one that gets violated the most often. It's all about inheritance. And it asks a really simple question. Does your child class really behave like its parent?
This is the L, the Liskov substitution principle, or LSP. The whole idea is that you should be able to take any child class you create and swap it in for its parent class anywhere in your code without causing any errors or weird behavior. That swap has to be absolutely seamless. And here's the real key insight. Inheritance isn't just about sharing code, it's about sharing behavior. A child class has to honor the contract, the set of expectations that was established by its parent. If it breaks that contract, you don't really have a true parent-child relationship, and, well, your application is probably about to break. This slide shows a classic violation perfectly. So, step 1. Our code is written with the expectation that any account object can be withdrawn from. Step 2, we pass in a fixed deposit account. Now technically it is an account, but its behavior is different. You can't withdraw from it. So in step 3, when the code inevitably calls withdraw, we get to step 4, boom, a crash. The substitution failed the test.
We're on the home stretch. The final 2 principles, I and D, are really all about the same goal: breaking dependencies and creating clean boundaries in our code. And the main tool we're going to use to do that is abstractions.
So, have you ever implemented an interface and then found yourself writing a bunch of empty methods or methods that just throw a not implemented exception? Yeah, that's a classic code smell. We call it a fat interface, and it's a sign of a problem.
This is what the interface segregation principle, is all about. It says that our code shouldn't be forced to depend on methods it doesn't actually use. On the left, our poor square class is stuck with this big shape interface, forcing it to deal with a volume method that makes no sense. But on the right, we've split up or segregated the interfaces. Now our square only needs to care about what's relevant to a 2D shape. Much cleaner.
And now we've come to our final, and you could argue, our most powerful principle. The problem it solves is a big one. It's when your high-level business logic, the brains of your application, gets hardwired to low-level technical details like one specific database. That kind of dependency makes your core logic really brittle and incredibly hard to change down the road.
There's a great saying that really connects this all together. If being open for extension and closed for modification is our ultimate goal, then this next principle is how we actually achieve it.
This is the D, the dependency inversion principle. And the key word is inversion. Look at the arrows. Before, the high-level user service directly depended on the low-level MySQL database. But afterwards, we literally invert that relationship. We introduce an abstraction, in this case, the database interface. Now, both the high-level service and the low-level database depend on that central abstraction. The technical details now depend on the business logic, not the other way around.
A fantastic way to wrap your head around this is the CEO analogy. A CEO doesn't go around telling individual developers what to do. That would be chaos, right? Instead, the CEO communicates what they need to a manager. That's our abstraction. The manager then handles all the specific implementation details with the developers. This completely decouples the CEO from the day-to-day work, which means you can swap developers in and out without ever disrupting the high-level strategy.
So, we've made it through all 5 principles. But the real power of Solid isn't just about memorizing a bunch of rules. It's about adopting a whole new mindset for how you approach designing software.
So let's just do a quick recap. S is all about focus, one job per class. O is about being safe, extend, don't modify. L is about reliability. Subtypes have to behave like their parents. I is about being lean. Small, specific interfaces are best. And D is about decoupling. Depend on abstractions, not on the nitty-gritty details.
But maybe the single most important takeaway from all of this is that solid principles are guides. They are not rigid laws. There's always a trade-off between a perfect design and the practical needs of the business. The goal isn't to apply them blindly everywhere, but to use them as a compass to guide you toward building cleaner, more scalable, and, ultimately, more maintainable software. So as we wrap this up, I want you to think about your own code. Think about that one class that's a total nightmare to change, or that fragile inheritance structure you're afraid to even look at. Which one of these principles could be the key to fixing it? Which one will help you start building code that's truly built to last? Thanks for joining us.